Perfect.
Yep.
Okay, good. Then I go on.
Go ahead.
What I will present is our activities in 3D inkjet printing, and I think it's a quite obvious part of functional fluid jetting, because what we are doing is always digital additive manufacturing. So the 3D printing is actually to print the object in the final application and not doing rapid prototyping. And you can imagine that if the printed object is used in the final application, the requirement towards functionality of what you have jetted is much more complex and challenging. Before I dig into the science and showing a little bit more technically, I just take a few moments to present myself. So I'm speaking from a Chemstream, and Chemstream is a small independent chemical R&D company. So it's a quite atypical profile. We are not ink manufacturer or printers. We actually, our business is to do research. And our core competence is actually to develop innovative new materials based on sustainable chemistry. And we do this not only to invent new things from the design phase, but also up to industrially prototype scale. So it's important that what we develop or what we invent can industrially be applicable. The core activity, so our business is a lot innovative contract research, which means a company comes to us and asks us to develop a certain material, a certain ink. And obviously we only do this, or usually only do this for non-standard requirements, so things which are not existing yet. So that's why a lot of the focus is to research really new things. We don't only do the formulation work, but also synthesize new molecules when it's needed in projects. So new monomers, new surfactants, new polymeric dispersing agents, as you just heard before my talk. And we try as much as possible to do this on bio-based raw materials. And it's, let's say, a long-term development that we do. What are our main deliverables? Obviously, first of all, inkjet inks, otherwise I would not be here today. And a big part of that is nano dispersions, so inkjet grade nano dispersions. And that's important for functional fluids because you have to integrate the functionality in the particles very small, very well dispersed, and it's a large activity of what we do. And then the last thing, and it's a strongly growing activity for Chemstream, is 3D printing materials. So it's the inks in order to be able to print a 3D object at the end. And I will focus a little bit on that. We just have celebrated our 10th anniversary. So we have started with 3 founders, and let's say we have a healthy organic growth. Today we are with 14 people. A lot of focusing is, of course, chemistry with mainly researchers. We're located near Antwerp, and in the meanwhile, we have a quite nice lab facility, so we can do organic synthesis, chemical formulation, and quite a lot of characterization methods, not only to analyze materials, but also to support our own development. Also important is that we don't only do very small scale, we have also a facility to produce, let's say, some batches. You see the volumes of a batch that we for the moment can produce. This helps us to support the customer up to the industrial pilot scale, but also for some application, we continue to produce it at the demand of our client for example, confidentiality reasons or quality reasons, that we continue to produce it. It's not our main activity, but we are, let's say, investing for the moment to be able to also make larger scale batches, but it will always be small volume, high added value applications, not mainstream inks. Inkjet printing, so when we say that we develop a new ink, crucial and central to that is the printing units that we have. And we have, in the meanwhile, 6 of these modular printing units, so we call them MPUs. What is it? It's an open printer. It's developed and manufactured by VDW, so Werner van de Winkel. It has a completely open interface, so you really choose where you lay which drop. You have, let's say, easily removable printhead module, so it's compatible with, let's say, the main industrial printheads, Xaar, Toshiba Tech, Konica Minolta, Kyocera, Samba, you name them, you just put another module there. And then important, you see maybe here, the little ink pot here in the middle. It's easy to exchange one ink to the other. So for some projects, we exchange up to three times in one day, one ink to the other. And so it allows to test a lot of inks and to optimize them. always keeping in mind the process of the final application. So usually the customer has already an industrial printer or designing it, and we can mimic what he's doing as well as possible on these printers. And that's very important, how you print with which printhead, but also how you cure, what is the distance between the difference, what is the time. So that's why we have a lot of these printers, really to do research, not to do production. Recently, we have invested in, let's say, high resolution 3D printers, which then allows to print really dog bones and other things. It's always with the same idea to be able to screen and test a lot of inks. Let me come really now into the technical part of 3D inkjet printing. I think this slide is very obvious, but helps us. It's a small animation. I hope it will work online. So that you can afterwards understand more in detail what are the challenges and opportunities of this technology. So what you do is just to print here with one printhead, one layer. And if it's a UV curable, you cure it, you come back with your table, then you go down with one layer. And typically the wet layer thickness, which is the same as the dry with UV curable, is between 5 and 25 micrometers. You print again a layer, and then you cure it, and you do this on and on up to you have the object which you want at the end. Usually it's or UV curable or a phase change ink. You have some applications with water or solvent based, but you can imagine if you have always to evaporate the solvent of the water, it's difficult to build up an entire object. Now you need, for most applications, at least 2 printheads, because you want to have an object ink, which is in the object printhead, and a support ink. And in this case, the support ink is also a UV curable. You print it at the same time as the object, but you can directly see that you can then create geometries which could not be printed without a support ink. So the support ink is only there as a temporary support of what you have printed as an object. And at the end, you see here maybe the support fading away. You have only the object. Where we have focused a lot during the last years is to have fast dissolving water soluble support ink. So usually it's or alkaline soluble inks, or you have phase change inks that you have to melt away. We have developed UV curable inks, which afterwards can very quickly and easily be dissolved in water. We, by the way, also use them for other kind of applications. But let's say the original development have been done in this concept. Where it becomes very interesting and quite unique is that you cannot use only one printhead, but as traditional 2D printing, you can print with different printheads, so with different objects. And you can start to make multi-material printing with objects, for example, with inks with different mechanical properties, so interwoven hard and soft, but also embedded functionality. And there you can create objects which are just not possible to be created in any other way. So there it's really, let's say, a new area, we believe, in material development, which opens with these kind of approaches. I come now because I focus now on 3D printing, and then you know a lot of other 3D printing technologies. So the question is, obviously, why would we do this with an inkjet? And you have, let's say, 4 very important reasons. First of all, is a high resolution. So compared to other traditional 3D printing, is the highest resolution, which is possible. You can create optically smooth objects, which is important for optical objects, so which is a big part of our development and research. Multi-material, I already mentioned that. And then you can have a very high productivity. And that is often forget because you see this small printer going up and down. You think, okay, it will take hours before you have your final object. We are working with a company who has developed in a smart way an inkjet printer, a circular printer, to allow very high productivities. And to give you an idea, by parallelizing a lot of processes within one printer, you can produce something like, for example, the size of a watch every 30 seconds. So that's really a new area, and we focus on digital additive manufacturing, which means for large industrial scale to produce the parts by inkjet printing becomes possible. And you have already these first printers now on the market. I will now focus on a few, let's say, case studies or things we have experience on, and then I think I can highlight challenges and things that you have to keep in mind once you want to develop an ink for a 3D printing application. One of this is, as I said, optical applications. So, for example, the printing of lenses. And here you print without support ink, but you use the fact that you can have this flow of these inks and that you have optically smooth surfaces without the need of a mechanical polishing step afterwards. So you can print this lens and it comes as that out of the printer based on these inks. Of course, if you want to design an ink for this application, transparency, low yellowing, and for UV curable that's not obvious is crucial. So you really have optimized photoinitiators, stabilizers, and actually every ingredient that you take has an impact on this transparency and yellowing. So you have to take all these things into mind. Very important also is overprintability. What does it mean? You take one layer, you cure it, and then you put another layer on top of that. And the second layer has to wet very well on the layer which has just been cured. And people who are experienced in 3D printing with, or just 2D printing with UV knows that this is a quite challenge. So you have to balance the wetting agent and the entire formula in order to be able to have this very high overprintability. And of course, then you need to combine mechanical properties and refractive index for this application. We are now focusing more and more, besides these ophthalmic lenses, on micro lenses, so small optical objects. We are creating now inks with very high, for us very high is above 1.6 or very low, below 1.4 refractive index, so by choosing the right monomers. And then you can think of creating optical objects with completely new optical properties, for example, these gradient index lenses, which you could not produce in any other way. So by voxel-wise, so 3D pixel-wise, put the refractive index at every place as you wish. And for this kind of research, it's important that you have the possibility to also synthesize new monomers. You can go up to a certain point with commercially available monomers, but to really reach these high and low refractive index extremes, you have also to synthesize the compounds which are really needed. So to combine the low viscosity with the optical properties which are needed. Another, let's say, application on which we develop different inks is 3D printing of reactors or bioreactors. And here you see that the challenge is, for example, to create this very small challenge. So you need a support ink which can be dissolved easily in order to be able to make these small challenges. And then you actually work in these kind of applications on microfluidics. So for biological applications, you need cells which are going through the channels, but it can also be used for, let's say, traditional microfluidic applications. And again, you can ask yourself, why would do this? You do this with 3D printing. Of course, you can create new shapes, new kind of geometries which just cannot be produced otherwise. And Inkjet then combines this high resolution, but also multi-materials. So you can have channels with hydrophilic, channels with hydrophobic surface area. So it's a kind of play tool. Multi-material printing, which is also, so you have obviously embedded functionality. So I write here inkjet grade nano dispersion. So whatever kind of functionality you can imagine, you can put it in the ink and print it. Here it's an example, an illustration of a fluorescent ink. But also very important is to reach the mechanical property. Almost every application needs a certain desired mechanical property, be it very soft or very hard. And there we have worked in the past years on that, and I go a little bit deeper than how we look at that. So we look at this very chemically. So you look at the ink, which is UV ink after cross-linker, after being cured, I mean, you have this kind of polymer network and you have monomers and cross-linkers in that. And you have to look at the molecular toolbox in order to obtain the mechanical property that you need. And it's too much into detail for these 15 minutes, but just as an illustration, you can look after that afterwards, maybe more in detail, but you can make cross-linkers which are very hard or very soft to make harder or soft materials. Another obvious thing is to take monomers with a low or a high TG, and then you can also tune the mechanical properties by choosing the right combination. You see that it becomes very complex, and one approach that you have to do always here is to do design of experiments. So what it means is that you have to combine different mechanical properties. You want to have a hard material or soft material with a high or low TG, etc. And then you have usually 5, 6, 7 different ingredients in that ink, which are all necessary. And then you think, okay, what is the optimal concentration? And then you can do it with molded parts, but usually it's different than when you print it. And then with these modular printing units, you actually can print a lot of different inks, and then doing design of experiments, and really, as illustrated here on the left, with a mixer profile, say, well, here in the middle is for that application my optimal concentration. The last thing that I will show is, I think, something which is quite tricky for people who have been involved in 3D printing knows that, is the creation of a dog bone here by Inkjet, so printed dog bone with an elongation at break above 400%. So it's a very flexible material that you can print, just to show you that usually Inkjet printed objects are known to be brittle, to be hard. But today you can, by rightly choosing the cross-linker, the monomers, the photoinitiators, etc., create materials after printing with broad variety of mechanical properties. I'm already at my last slide. I invite you to visit our website. You can contact me. I have here my email. We have also our general email address. And then, Amy, I will send you the presentation that I gave you so that everybody can share it afterwards. So excellent. I think we have a few minutes to, if there are some questions or things to be answered.
Thank you very much, Marin. That's very interesting. Yeah, does anybody have any questions? Now's a good time to ask if you do.
What type of print heads do you generally use for your applications of 3D printing?
Mm-hmm. It really depends on let's say the functional fluid. I will give you a few examples. For optical lenses, we have worked a lot with the Konica Minolta KM 1024, now the 1800i print head, for different reasons, but certainly combining this high resolution and very small, the 3 picoliter tools allow for optical application to be very precise. And since most of these optical inks are clear inks without high pigment loads, you don't really need this true flow print heads. That's for one example. We have other applications where we use XAR or Toshiba Tech print heads when we need a high concentration, for example, of pigment loads. And certainly both XAR and Toshiba Tech have also these possibilities to put relatively big layers. For example, in our lab, to print these dog bones, we use the T-Tech print heads, because it allows, they have these XL print heads with up to 180 picoliter drops. And then you can build up relatively quickly in an R&D environment dog bones with 4 or 5 millimeters so that you can test it. That's, yeah, a few examples of what we are using.
That's good. Thank you. Thanks very much.
So I had a question, Marin. You mentioned a dog bone that you were testing. Has that actually been used for that application, or is it a kind of an example?
Dog bones are always actually we have a tensile tester internally, so it's actually the shape that we print in order to evaluate the mechanical property. So we evaluate the tensile strength, the elongation at break, and the E modulus with these dog bones. We don't have any application where the customer at the end wants to print dog bones. Dog bone is also only an illustration. We have also blocks for HDT. I mean, you have different kind of testing materials. So yeah, it strongly depends on what is the requirement. But the final application usually don't print dog bones. But yeah.
Okay, understood. Yeah, it's certainly very impressive seeing that elongation with a printed structure. So.
Mm-hmm. Yeah.
Okay. Any other questions for Marin? No? Okay. All right. In that case, we'll thank him and Chemstream very much, and we'll move on to the next presentation.
Thank you. I will